All right, let's go ahead and do this warm-up then, see how you did, and then we'll jump into the last part of this section. So the cat has dropped from a 100-foot tower. Its height is modeled by h of t. What is its average velocity? So velocity and speed, very similar, but velocity is directional. So we're going to go ahead and label this on part A. We'll label it average, which you could abbreviate AVG. And instead of ROC for rate of change, the rate of change of height or the rate of change of position is called velocity. So we're going to call it average velocity, and you can abbreviate that VEL. So remember, you want to show the difference quotient. So during the first second, that's on the interval, if you want to write it, T epsilon 0 to 1 beefy bracket. So that's one way I can give it to you, or you can write it like this, remember, from 0 to 1. Both of those mean the same thing. So during the first second is from 0 to 1. So for average rate of change, there always has to be two x values, or in this case, two time values. It's going to be the height at 1, its ending height, minus its height initially at 0, all over the change in the corresponding x values. So that's the difference quotient. If this were a quiz, that's what I would expect to see. Okay? And let's think about what the units are going to be here. Units of height is feet. Units of time is in seconds. So if you put the units in there, you can kind of use dimensional analysis or stoichiometry if you want. And then feet divided by seconds, of course, is feet per second, which is how we measure velocity. So now when we evaluate this, we'll plug in the 1 in for t up here, right? Just plug in the 1, and you get negative 16 plus 100, negative 16 plus 100. And then minus, you plug in a 0 for t, and you get 100. You get 100. And then, of course, 1 minus 0 is 1. So notice I didn't go ahead and say negative 16 plus 100 was 84. And I certainly didn't say it was like 86, right? Because what's going to happen with your 100s? They should cancel, right? When you drop the parentheses on the top, you get negative 16 plus 100 minus 100, which gives you negative 16 over 1. And then the units are feet per second. Okay? And so that's the answer. It's the numeric answer, and there's units, so you always want to include units in your final numeric answer. But the fact that it's negative, that doesn't mean the cat's falling backwards, does it? That'd be kind of cool. It's falling down. That's the direction, okay? Here's how you can actually write it, okay? We're going to go ahead and practice our sentence again. So we start with that introductory adverbial clause. From t equals 0 seconds to t equals 1 second. Or you could say, as I gave it to you, during the first second. That would also work, okay? But you need units there, comma. Here's the one way to say it. I'll put a little bullet here because we'll do it a couple of ways. The cat's height is decreasing. The cat's height is decreasing. How do I know that the height of the cat is decreasing? It's falling, right? And we know how gravity works. A cat knows how gravity works, I guess. At least this cat does. But because the answer is negative, right? It tells you how the quantity is changing. It's the average rate of change. So the cat's height is decreasing on average. On average, we have to throw that in there. 16 feet. So we answer it in units of height, and then we actually write it per second. And in this case, I'm going to put it like that. Instead of PER, I think it's appropriate today to write it as PURR, right? Because it's a cat. 16 feet per second. So that's one way to do it. Or you could say the cat's average speed. Let me spell average correctly. The cat's average speed is 16 feet per second. And notice I'm answering that now as feet diagonal second instead of writing out the word per. And then we would say in the downward direction. In the downward direction. Either of those are correct, but notice they're kind of emphasizing something different, right? Velocity is a vector. They both kind of interpret the sign. The cat's falling downward, or in the second one in the downward direction. One of them is talking about the height decreasing, and the other one's talking about the speed on average. They both mean the exact same thing. Okay? The cat survives, of course, right? Any comments or questions on that? Pretty nifty. What would happen if we were dropping the cat from 1,000 feet? Would the average rate of change of the cat during the first second be any different? No, it's independent of the height, right? Because if you notice in the numerator, your initial height is 100. They're always going to cancel out. As long as you're near the surface of the earth, gravity is going to affect falling objects. You know, of course, neglecting air resistance and, you know, cats sprawling out to make themselves, yeah, whatever. Things are going to fall at the, accelerate towards the surface of the earth at the same rate. Okay. Thank you, Kat, for your participation. No cats were harmed in this math problem. All right, sweet. Let's go ahead and jump into the next part here of this section, which is looking at symmetry of functions. That's another property of functions. Remember, this section is just blandly labeled other properties of functions. Symmetry is a very, very important one because if you're trying to sketch a function and you know a certain graph or equation has symmetry, then you could actually get the rest of the graph by only having part of the graph. All right, and there's two types of symmetry that we're going to be looking at. The top one, if you notice, appears to have what type of symmetry? This one here. Y-axis symmetry, right? If you were to fold your iPad on the y-axis, it would break and you would be incredibly strong and I would send you to the hub. But if you were to do it virtually, you would see that the graph would perfectly coincide with itself. Y-axis symmetry. Okay? Fold it, lines up with itself, it's a folding symmetry. Any function that has y-axis symmetry, we call an even function. So the two descriptions are interchangeable. An even function has what type of symmetry? Y-axis symmetry. A function with y-axis symmetry we refer to as what type of function? Even. Okay? They're interchangeable. The other type of symmetry that we're going to be interested in, there's only two types. Not y-axis symmetry, but not x-axis symmetry. Y'all took the bait, right? Fish on a hook. I'll throw you back, right? It's catch and release here. Why not x-axis symmetry? Why do you think not x-axis symmetry? Let me draw something that has x-axis symmetry. It wouldn't pass the vertical line test, right? So we don't really look for x-axis symmetry. In fact, there is only one function that has x-axis symmetry. That's still a function that passes the vertical line test. Can anyone think of what it is? What kind of straight line? A vertical line wouldn't work. You were making your line vertically because that would fail the vertical line test, right? Nothing fails the vertical line test. A horizontal line. Very good. Very good. The x-axis itself, which is y equals 0. That's the equation, or f of x equals 0. That's the only function that has x-axis symmetry because it is the mirror itself across which things can reflect. Okay, so that's kind of a trivial case. Any other function that passes the x or that has x-axis symmetry is not going to be a function of x. So the other one that we're going to look for, get rid of that, is actually not a folding symmetry, but a rotational symmetry. So if you look at this graph here, imagine like putting your finger down at the origin like a spinner and then flicking that graph and then stopping it after it rotates 180 degrees, right? Or just take your iPad and turn it upside down, right, 180 degrees. Does the graph appear to be the same if you rotate it 180 degrees about the origin? The answer is yes, it actually does, okay? But if you were to move this graph, let me go ahead and trace over it kind of poorly. If you were to move this graph up, would that graph have rotational symmetry through the origin? No, because when you rotate it, it's going to end up down here now. It's going to end up down there instead of at the origin. So, no, that one wouldn't. But the one that passes through the origin would, right? You turn it 180 degrees, it coincides with itself. So this would be a rotational symmetry. Rotational symmetry about the origin. We just call it origin symmetry. That's what we call it. It is a rotational symmetry, but we just call it origin symmetry. Now, any function that has origin symmetry is going to be called an odd function. And oddly enough, that one's not bold, like the one up here was bold. That's kind of odd. I don't know. That's just me overlooking it. Now, there's an easy way to remember which one's which, right? An even function has y-axis symmetry. Those kind of don't even rhyme, right? Y-axis symmetry, even function. Does that make it easy to remember if they don't rhyme? No. Well, what about origin symmetry being odd functions? O and O, right? Very perceptive. So there you go. An odd function, not peculiar function, right? Odd function is origin symmetrical. Origin symmetrical, which is rotational. There's an O in rotational as well, right? So if you forget that origin is rotational, look at there. There's just a plethora of O's there, which when you put them together is ooh, right? If you break them out of the letters, you put them together, it's ooh. And if you put a B in front, now you're celebrating October, right? Okay, good. I don't know where that came from. I'll try to stay on task here. All right, so we have two types of functions. And if you have the graph, it's pretty easy to determine if a function has symmetry or not, yeah? You just look at it, and you can imagine folding it or rotating it. But guess what? We're not always going to have the graph. In fact, we want to use symmetry to help us sketch a graph. So we're going to figure out a way, if there is a way, to determine from the equation if a function is even or odd or neither. You think we could find a way together? There's a need for that. We should probably invent a way. Okay, so let's come up here and let me get that annoying cursor off the screen, right? I don't want to be that teacher. There we go. Move. There we go. So if a function is even, it has what type of symmetry? I forgot already. Y-axis. Okay. So here's the algebraic consequence of that. If you plug in a positive x or a value of x that is equally the same distance from the y-axis but on the other side, like 5 or -5, 10 or -10, 1 or -1. Because the y-axis symmetry, what should we know about their y values? They should be the same. Okay? So here's the algebraic consequence. F of -x should equal f of what? F of positive x. That's the algebraic consequence. Plug in a negative value or a positive value. Their magnitudes are the same. So they're the same distance from the y-axis. You're going to get the exact same y value. The y value can be positive or negative. But that's the algebraic consequence. All right, so if, we're going to add this here now, if that equals that, then f is what? Even, odd, or neither? Even. Okay, so we just came up with a little theorem. Now I'll show you how we can algebraically test for that. But that becomes kind of our test for an even function. All right, let's jump down here. If it's an odd function, then I plug in an x over here and I get this y value. Now if I plug in an x that is equal in magnitude, but on the opposite side of the y-axis, because of the origin or rotational symmetry, I'm not going to get the same y value. What am I going to get? The exact opposite y value. So let's come up here and say then if f of -x equals not f of x, but what? The opposite. We can read that negative in front as the opposite of f of x. Then we know that f is odd. Not peculiar, but odd. It's an odd function. It has origin symmetry. So this now becomes our test for odd functions. And of course then if f of -x does not equal f of x, if it's not even, and if f of -x does not equal the opposite of f of positive x and it's not odd, then it must be what? Neither even nor odd. It could be something else, right? But it's not going to have y-axis or origin symmetry. Let's try it out, shall we? Yeah, let's do that. Example 6. Determine algebraically if the following functions are even, odd, or neither. Verify graphically if possible. Ooh, okay. Let us try it. Example 6a. F of x equals -x squared plus 5. You probably already envisioned that in your head, right? I can't stop you from seeing that parabola opening down in your head with the vertex at 0, 5, can I? In fact, if I tell you not to think about it, you're probably going to think about it, right? Yeah. They say there's two ways to get things done. You either do it yourself or you forbid your teenager from doing it, right? So, okay, good. But let's pretend like we have no idea what it looks like. Here's the test, all right? I'll go ahead and put test here. We're going to test it for symmetry. The good news is we start the test for even or odd the exact same way. That is, we replace x with negative x. We replace x with negative x. And we look to see what happens on the other side. So remember the first day I told y'all that when you have an x, it's a wise thing to replace it first with parentheses. And of course, if you've been working my favorite problem, you know exactly why that's important. So in for x now, we are going to replace negative x. See that? Now all we have to do is work straight down and simplify. Do these negative times a negative make a positive? Is that how we do this? Evaluate that? Remember your dear Aunt Sally, PEMDAS. We have to square it first, right? Exponentiation comes before multiplication. So working straight down, what is negative x quantity squared? That's the same as positive x squared, right? And then the negative is still in front. Okay, we've simplified it about as much as possible. Now all we do is we compare it back to the original, and we ask ourselves, self, is it the same that I started with, or is it the opposite of what I started with? And of course, in this case, we could say it's the same. So we're going to finish this off with equals f of x. And notice what we've done. Now, algebraically, we have said f of negative x equals f of x. And we've just completed the test. And so now we write our conclusion. You could say therefore. Therefore is kind of a cool symbol, right? It's a little triad of dots. Or you can write out the word therefore. But you know what I like to put? Of course, you've seen it before. My good transitional word is so. Right? It's only 2 letters. It's pretty short. You can also write ergo, which means therefore. Or you can put the 3 dots, whatever you want. But we're making our concluding statement. So, f, or f of x, right? The name of the function is f. F is what? Even. Yeah. Which means we know it has y-axis symmetry. All right, so again, to confirm graphically, it's a parabola that opens down because the leading coefficient is negative, and it's shifted up 5 units. So there it is. There it is. Okay. Boom. Y-axis symmetry. We kind of knew that in advance. It's good to verify it. Now we know the test works. Okay? Any questions on that? Sweet. So why would that be important? Well, let's say we didn't know what this graph looked like in quadrants 2 and 3. For some weird reason, we're like, all I know about this graph is that part right there in 1 and 4. But I also know it's an even function. Like, hey, if it's an even function, and you know what the graph looks like in 1 and 4, how do you get the rest of the graph? You just reflect it across the y-axis to get the other half. Oh, that's pretty cool. That's like 2 for 1. Or half price sale and you buy 2 of them. Right? All right, letter B. Uh-oh, this is another parabola. It opens what? Up, down, left, or right? Up. Does that mean it has y-axis symmetry? Not necessarily, right? If you have a parabola and it opens up or down, but it still has its vertex on the y-axis, is that going to mess with the symmetry, the y-axis symmetry, if you move it up or down? No, it won't, right? It still has y-axis symmetry. If I just move it up or down, will it mess with y-axis symmetry? No, but if I move it left or right, does it? Yeah, now that messes with the symmetry. So here's what's kind of interesting to note. If you have a vertical shift, which is just your constant at the end, does a vertical shift affect even functions? Does a constant, in other words, affect even functions? No, right? Because we're trying to plug in a negative x and get the same thing we started with. And if you have a constant like +5, do constants change? No, that's why they are appropriately named what? Constants. Sweet. All right? But if you have a horizontal shift, and if you remember completing the square on a parabola, you know that having an x term shifts the parabola left or right. That should affect the symmetry of the graph, yes? So if I had to guess if this one had y-axis symmetry, I would probably say no. But let's verify. All right, here we go. Test. We're going to say g of negative x equals, and there's 2 x's to plug into, so it's going to be quantity negative x squared minus 4 times quantity negative x plus 3. There's the plug-in step. And now once we plug in, all we do is like the Marine Corps, simplify, do or die. I think that's their motto. Simplify, do or die. Or something like that. What is negative x quantity squared? Just x squared. And then negative 4 times negative x is positive 4x, and then we got plus 3. Cool. Now we compare it to the original. Hi, Coach Fair. Is it the same function we started with? No, it's not. Is it the opposite of the function we started with? No. How do you tell quickly if it's the opposite of what you started with? Everything is opposite sign. Good. If it's an opposite function, every sign will be the opposite sign. We have two signs that stayed the same, but one sign that didn't. So that's going to be neither. So you could say this doesn't equal g of x, nor does it equal the opposite of g of x. Okay? So g is neither even, and then what do we use for our conjunction? You don't get to use it that often. Nor, right? Neither, even, nor, odd. It's a neither function, as we probably anticipated, because it takes a parabola that opens up, that has y-axis symmetry, and the x term shifts it in a certain direction. So that messes it up. Okay? So horizontal shifts can mess up even functions, but vertical shifts do not. The plus 3 was okay. It had the same sign. All right. You want to complete the square and figure out where that is? We don't need to, right? Okay, good. Let's just say today, on Columbus Day, it's just not possible. Okay? Time constraints. All right, letter C. We got h of x. Oh, by the way, let's come back over here. What do you notice about the powers on our two variables there? This one was, remember, if there's nothing showing, it's implied to be a 1. Okay? The x squared was not a problem, was it? For an even function, the x squared was not a problem. Because when we square a negative number, it returns to its original state. And that's what we're shooting for even functions. But an odd exponent is significant, right? Because that changes the sign. So even exponents do not change signs. When you square a negative number, raise it to the 4th power, it keeps the same sign it was originally, whereas odd exponents do change the sign. Any connection then to why we call them even or odd functions? Let's look over here. We only had one variable, and what type of number was it? Even, odd, or neither, the exponent. It was even. We only had one variable, and the exponent was even. What type of function did we have? An even function. On this one, we had a combination of both even and odd exponents. What was our conclusion? It was neither. So what might you suspect over here on h of x about 2x cubed minus 3 if there's only one variable and it's an odd exponent? What might you think? You might think that it's odd, right? Let us see. Let us see. Here's the test. H of negative x. It is 2 times negative x cubed minus 3. You got to have the negative x in parentheses. All right. Now we work straight down, lining up the equal sign, and we simplify. What is negative x to the 3rd power? Does it change the sign, or does it just keep the original sign? Well, if you raise a negative to any odd power, it's going to stay negative, right? Which means it'll change the sign. So that first term becomes negative 2x cubed. Negative x times negative x is positive x squared, but times another negative x makes it negative. And then we have this minus 3, which is a constant. We compare it to the original. Is it the same? It is not the same, so it's not h of x. Is it the exact opposite? Do both signs change? No. It's not equal to negative h of x either. So h of x is what? Neither, even nor odd. We thought it was going to be odd in the beginning, didn't we? Because there was only one variable and it was on exponent. But we know why if we think about it. If we think of the parent function, 2x cubed. Remember, the parent function is x cubed, which is the discograph. The 2 does what to it? Vertical stretch, right? Just a little smidgen, a little steeper. But the minus 3 does what? Moves it down 3. Oh. And if you vertically shift what was previously an odd function, is it still an odd function? No, because when you put your finger down at the origin, that other graph is now going to be up here. So do vertical shifts interfere with even functions, with y-axis symmetry? Do vertical shifts interfere with even functions? No, no. Vertical shifts do not. Horizontal, yeah, but vertical, no. Do vertical shifts affect origin symmetry? Absolutely they do, okay? Oops, I didn't get the whole thing. There we go. See that? That is origin symmetric, but if you move it up or down, it's no longer. So vertical shifts mess up origin symmetry. And we can see why. Because if we want it to be origin symmetric, we want it to be an odd function, which means we want to end up with the opposite of what we started with. That also starts with O, right? Opposite, origin, odd, which means we need all the signs to change. And if we have a constant, are you going to change the sign of a constant? No. Even if he changed his name to like Mr. Changey Pants, he's still a constant, right? Changing his name doesn't change what he is. Kanye or Ye or whatever he is. Ye, Z, okay. So that one's going to be no. All right? That one's going to be no. Constants interfere with origin symmetry, but not y-axis symmetry. All right, let's look at letter D, V of t now instead of y of x or f of x. Look at your variables. We have to the third power, which is what type of number? Odd. We have to the first power, which is what type of number? Odd. Odd. So just thinking ahead without doing it, if I plugged in a negative t to both of those letters, will both signs change? If you raise a negative number or a negative value to an odd power, it's going to change the sign. So both signs will change. Do we have a constant here that's not going to change? No. So if both signs will change, we're going to get the opposite of what we started with. This function should be what? It should be odd. Yeah, we're guessing odd in advance. Now let's do it. Test. V of negative t instead of negative x. We're going to get a negative 1/2 quantity negative t cubed minus quantity negative t. Parentheses, parentheses, parentheses. Okay, so good so far? Oh yeah. All right, working straight down. A negative t cubed is going to be negative times positive t cubed, which that negative out front is going to make that a positive 1/2 t cubed. This negative and this negative combine to make it positive. It changed the sign. This negative times negative also changed the sign. Okay, so that's plus t. Now, if you compare it to that one there, it's not the same. Okay, so it is not equal to v of t. So you could say that arrow means kind of therefore, or I'll just do this. I'll keep it. So v is not even. Okay, you're not going to even have to show that eventually, but that's us going through our checklist. Now, is it the opposite? The answer is yes, it's an opposite. Here's all you have to do to prove it's an opposite. All you have to do is factor out a negative that's already there. Now, what happens if you factor out a negative from every term? What does it do to every term? It changes the signs. So if we factor out a negative, we're left with negative 1/2 t cubed minus t. And you can mentally see that if you redistribute that negative, you get what we have on the line above. Well, because this right here is v of t now, this ends up being the opposite of v of t. So you see what we did there? We replaced t with negative t. We simplified it. It wasn't the same. But if I then factored out a negative from every term, it is now the opposite of what I started with. Okay? Which now we could say so v of t is odd. It has origin symmetry. Okay? So I do want you to be able to go through the test with the right notation. But the real thing that we're going to be doing here is just looking at a function and telling from a glance if it's even, odd, or neither. So let's kind of review. If you have variables and the only type of exponents you have are even numbers, whether there's a constant or not, the function should be what? Even, right? But if you have a combination of even and odd exponents in a function, that's going to mess it up. A combination of even and odd, that's neither even nor odd, okay? This is the one you have to be careful. If you only have variables with odd exponents, will it automatically be an odd function? No. If it has a constant, it ruins it. Vertical shifts ruin origin symmetry. But if there is no constant and all you have are odd exponents on your variables, then it should be an odd function with origin symmetry. Okay? So that's what we're trying to distill from this activity. All right, so now let's look at letter E. R of M. This function's name is Ronald of McDonald, or R of M for short. What's different about this one besides the R's and the M's? It's a fraction. It's a quotient now. It's a rational function. So, how can we do that? Well, we can do the same test as before and see. But notice the numerator, if you were just looking at M cubed, would M cubed be even, odd, or neither? It would be an odd function, right? It's just X cubed, but with an M. So I'm going to put O. If you were just looking at the denominator, what would that be? Just the denominator. It should be even, right? Constant's there, but that's not a problem. The only variable is an even power. So I have an odd function divided by an even function. I wonder what that's going to be. Neither? I don't know. Let's see. Test. You think it'd be odd? Let's see. Let's test it. R of negative M. So in the numerator, we're getting negative cubed. And on the bottom, we get 3 minus 2 negative quantity squared. So there's the plug-in. All right, in the top, if we simplify, we can essentially just drop the parentheses. Negative m times negative m times negative m is going to be negative m cubed. It's an odd power. The sign changes, okay? But in the bottom, it's just 3 minus negative m squared is positive m, so we just get that. Now notice, I'm going to do it off to here. This is not R of M. Okay, so instead of doing it on the line below, this might be a better place to do it. It's not R of M, so R is not even. Would you agree? Okay, so now the question is it the opposite of what we started with? Well, this one's a little bit different. You don't want to factor out a negative from both the top and bottom, right? Because look over here. What if you factored out a negative from the top and a negative from the bottom? What's going to happen with those two negatives? They'll divide out to make a positive. So if you have a fraction and you want to know if it's the opposite of what you started with, you only factor out a negative from either the top or the bottom. But remember, our goal is to try and see if it's the opposite of what we started. The denominator already looks the same, doesn't it? So let's do this. Let's factor out that negative from the numerator. It's like factoring out a negative 1. There's a square there. There we go. All right? So if I factor the negative out of the numerator, I can put it out front of the entire fraction. It's like having a negative 1 over 1 in the front. See that? This negative out front is like a negative 1 divided by 1 times that. Well, it's not negative 2 times negative m. It's negative m squared first. Right? We have to do the exponentiation first. And negative m squared is positive m squared. And then times the negative makes it negative again. So it stays the same. So if I just factor the negative out of the numerator, what am I staring at now inside these parentheses? Is that what I started with? That is, right? So this ends up being the opposite of R of m, which therefore means what? So R is odd. So I heard it. Someone guessed right or reasoned right. I don't want to say guessed. Someone reasoned correctly before we started. An odd function divided by an even function ended up being what? Odd. What do you think an even divided by an odd would give you? Also an odd. Very good. Why does that work? Odd functions act like what type of values? Yeah, negative values. When you're doing the test, they act like negative numbers. And even functions act like what? Positives, right? So you can say an odd number it acts like a negative number. I'm going to put a single squiggle. And then an even function acts like a positive. So you can use your rules of multiplication and division here. An odd divided by an even is now the same as a negative divided by a positive, which is going to be a negative or an odd. Flip it, it doesn't matter. A positive divided by a negative is still negative or an odd function. Very cool, right? And we just kind of verified that. So in the future, you could just look at this one and say, oh, I got an odd function on the top, I got an even function on the bottom. Odd divided by even is odd. This function has origin symmetry. Pretty neato mosquito. All right, letter F, Q of Z. Man, Q of Z. We had Ronald McDonald. This is not quite Queen B. This is Queen Z. What type of function do you see in the numerator? Even, odd, or neither? Remember, this is Z to the first. Odd, right? We got a odd power on the variable, an odd power on the variable, an odd power on the variable. Do we have a constant in the top? A plus a number? No. That would ruin the symmetry of the top. So the top is, in fact, an odd function. I'm going to put a single squiggles here. You could say that function is approximately. And then what type of function have we in the denominator? Cubed to the first, both odd powers. No constant again. So we have another odd function in the denominator. What do you reckon an odd divided by an odd is going to give you? An even function. Because that's similar to having a negative divided by a negative. And of course, a negative divided by a negative is a positive. Let's verify. Let's verify. You're right. It will be even. So now we're just verifying. Test. Q of negative Z. This one's going to be a lot of fun. 3 times quantity negative Z to the fifth minus 6 quantity negative Z cubed plus negative Z. All over 3 times negative Z cubed plus 4 times negative Z. So when we quiz over this, I do want to see the test. After we quiz over it then, you're going to just be able to look at it. I want you to know why things work. All right, so now if we simplify, in the numerator, it's pretty easy. All the signs are going to change. We're essentially pulling the negative ones out front. So negative 3Z to the fifth. This becomes positive 6Z cubed, and then minus Z. All over negative 3Z cubed minus 4Z. Now here's where you got to be careful. If you compare that to the original, it doesn't appear to be the same, does it? It doesn't appear to be the same. But because all the signs are changed in both the top and bottom, look what happens. If I factor a negative out of the top now, factor a negative out of the top, you get positive 3Z to the fifth minus 6Z cubed plus Z. And on the bottom, if you factor out a negative, you get positive 3Z cubed plus 4Z. And as I already mentioned, when you factor a negative out of both the top and the bottom, what happens with the negative divided by a negative? It becomes positive. So what are you left with? You're left with this highlighted piece here, which when you compare that to what we started with, is it the same? It is. All right, so negative divided by negative is positive. So this does actually equal Q of Z. Oops, Q of Z. So Q is what? Even. All right. So if I gave you a quiz, I would expect to see the test. You would kind of use maybe your intuition in the beginning, or now your analysis, to determine what the answer should be. An odd divided by odd is an even. Odd functions act like negative numbers. Even functions behave like positive numbers. Okay, let's do y of x now, but let's not do the test. Let's just see what happens. What do you notice about the denominator, even, odd, or neither? It's even, or neither. In the denominator. We have one variable to an even power. We have a plus 4. Is that going to mess up even symmetry, a vertical shift, a constant? No. Constants only mess up odd functions, not even functions. So we do have an even in the denominator. In the top, we have an odd power on an x, an odd power on an x, and a what? And a constant. Does that mess up origin symmetry? It does. If that 6 were not there, we would have an odd function. Let's see what that would be. This is not what we can actually, we can't do this on a test. It's like, I prefer that 6 not to be there. I'm going to work it as if it weren't. If it were not there, we would have an odd function. And of course, then an odd divided by an even would be a what? it would be an odd. But in this case, we have a plus 6. So instead of an odd function on the top, we have a what? We have a neither function. Ruh-roh. What do you think a neither divided by an even is? Right, this is going to be a neither function. If you have a neither in there, in a quotient, it kind of ruins the party. Don't invite neither to your party. He's a party pooper. Right? Everyone there is even, everyone there is odd, and then neither shows up. He's like, great. Great. Ruined everything. Neither. So, y is neither even nor odd. Neither even or odd. Now you could verify it on your own. What's going to happen is when you factor that negative out of the numerator, it's not going to be the same because it's going to change the sign of the 6, and it's not going to be the opposite because that 6 is going to mess it up. So you'll see that it's not f of y of x or negative y of x. All right, so you think you can handle quotients? Yeah, with quotients, okay, odds are negatives, evens are positive, neithers are atomic bombs, right? Boom, all right. Now, what if we get something like this? This is not a quotient anymore, but it's also not nice little polynomial exponents. What can we do? Any idea? Even, odd, or neither? Yeah, very good. We know that we could write this as 3 times the quantity, 8x to the 1/3 power, and now we have exponents. And, because it's to the 1/3 power, 3 is an odd number, right? So if I replace x with negative x, first of all, that's gonna put a negative under a radical. Is that going to be okay on a cube root? It should be okay, right? Let's test. When in doubt, just test it out. Actually do the test. So here's the test. Big F of negative x is negative 3 times, I'm going to go back to the cube root for now, 8 times negative x. All right. So if I simplify that, that's the cube root of. Now this is the same as negative 1 times 8x under the radical. Would you agree? 8 times negative x? Well, we know our properties of exponents now. We spent a lot of time doing that. That's the same thing as the cube root of negative 1 times the cube root of 8x. Now, we could take the cube root of 8. It's 2. But I want to try and compare it to the original. So the big question is then, and this is kind of what we were faced with in the beginning, what's the cube root of a negative 1? It's negative 1, right? We can have negatives under there. It's a negative 1. So that's going to change the sign and now make that positive 3 times the cube root of 8x. Okay? This negative here, when it becomes negative 1, gets with that guy. Now we can compare that to the original and be like, what? Is it the same or is it the opposite? It's the exact same as what we started with? It looks to me like it's, if there's only one term, for odd, remember we want all the terms to change sign. Did we change sign on the term? And everything else is the same? We actually did. We started with a negative 3 cube root of 8x, and we ended with a positive. That's the opposite sign, right? It's the opposite sign. It doesn't have to end up being negative. It just has to end up being the opposite sign. This is equal to the opposite of f of x. So what? So f is what? It's odd. Yeah, it's an odd function. All right. So what about this one up here? What do you think if I replace d with negative d to the 2/3, what's that going to be? That's the cube root of d squared. All over the square root of d squared plus 4. We're back to a quotient. If I replace both of these d's with a negative d, is the sign going to be the same or different? Will it stay the same or change? It'll change now, right? So both of my variables are even powers, which means when I plug in a negative d, it's going to be exactly the same. Is this plus 4 on the bottom going to ruin even symmetry? No. So guess what's going to happen? I'm going to end up with an even function over an even function, which is going to be what? Even. So P of D is even, exclamation point. And speaking of TD, touchdown. We just scored. We got through it. Yeah. All right. Tomorrow we're going to summarize by filling this in, and then we're going to look at piecewise functions. So we're going to finish this section tomorrow, okay? You got about 20 seconds until the bell. Enjoy the rest of your Columbus Day.